Hi everyone. So I want to keep going with the Fourier transform. We've been kind of working on some examples of Fourier transforms, and we know the formulas for the Fourier transform. And the idea now is basically how much mileage can we get out of this. So we have these formulas. We can always do these integral to get Fourier transform, but it's nice, integrals are a pain. It's nice if you can figure out a way to do a Fourier transform without doing an integral. Okay, so that's what I want to be focusing on in the next couple lectures. Is I want to figure out ways, how can you do Fourier transforms efficiently using things that you know without having to do these horrible integrals all the time. Okay, and that one of these things that I want to talk about today is called the Fourier transform duality, which is one way of doing that. So here it is. Here's our formulas for the Fourier transform and the inverse Fourier transform. And if you look at these, they look very similar. Capital F is the Fourier transform of the small f. And to get that Fourier transform, I do an integral, I multiply it by e to the I kx. And then put the other way around, small f is the inverse Fourier transform of the big F, capital F. And then to get the small f, I take the big F, I multiply by e to the minus I kx, do the integral, and then divide by 2 pi. So there's a few differences here. There's a 2 pi in this formula, but not in this one. And then the sign of the exponent is different. And the labels of the variables are different, but that's about it, okay? And so what I want to explore today is the fact that those formulas are similar allows you to do some other Fourier transforms right away in a simple manner. Okay, so let's get started with that. So maybe the first thing to do is look at some pairs of Fourier transforms. And some examples, which we've already discussed, are the delta functions. It's especially easy to see this symmetry when you're dealing with delta functions. So for example, so this will be the first example. Let's say f of x is equal to delta, the delta function, delta of x. What is the Fourier transform f of k? I just take this integral. Delta of x, e to the I kx dx. And the delta function is only active at x equals to 0. And so I get just e to the I k times 0, which is 1. So we have one Fourier transform pair, which is that delta of x, I like to write it like this, is a Fourier transform pair with the constant 1. In other words, if I have a delta of x and I take the Fourier transform, I get 1. Now let me ask a related question. What's the Fourier transform of f of x equal to 1? Okay, so in other words, suppose I just took a constant. I want to know what is the Fourier transform of a constant. Well, let's work it out. So f of x is equal to 1. And what is f of k? Integral minus infinity to infinity e to the I kx times 1 dx. And this integral, you have to remember, when you have an integral of e to the I something times x dx, that's a delta function with a factor of 2 pi. So this is 2 pi delta of k. Okay? So what we found is that we have another Fourier transform pair, which is like this. 1 and 2 pi delta of k are a Fourier transform pair. And maybe you can see what I'm getting at here, which is that, this thing, if I Fourier transform it, I get 1. And 1, if I Fourier transform it, I get the thing back again, right? Delta, 2 pi times delta of k. There's a difference when there's a factor of 2 pi sitting out there. But it's other than that simple numerical factor, doing a Fourier transform of something where I already know it is the Fourier transform of something, I can determine the answer very easily. It's kind of a mouthful. It's hard to say it in words. It's more obvious just to look at it, right? Anyway, I'll work on a little more. Let's do another example. How about this one? We already did this one. Let's say f of x is equal to a
sine of some number. I'm just going to call it k0 times x. So this is some number. Okay. What's f of k? We already worked this out, but let's do it again. Minus infinity to infinity, a, and then I'm going to write, for the sine, I'm going to write it in exponential form, 1 over 2i, e to the I k0x minus e to the minus I k0x, e to the I kx dx. Okay. So that's 1 over 2i times a. And then integral minus infinity to infinity, e to the I k plus k0 times x minus e to the minus I k minus k0 times x dx. Okay. And each one of those is a delta function, a over 2i. The first one is 2 pi delta of k plus k0 minus 2 pi delta of k minus k0, just like that. And let me simplify it. We already did this once. This is the two spikes, right, in the imaginary part of the Fourier transform. So this is f of k. There's a spike at k equals to k0 here, right? This is k0. And then there's a negative spike at k equals to minus k0, like that, okay? Okay, so there's another example. We already worked this one out. Now let me ask a question. What's the Fourier transform of this function, I pi a delta of x minus x0 minus delta of x plus x0? Where is that coming from? That's this function, right? So I'm saying, what if I knew that function is a function of x? What would be the Fourier transform of it? Well, let's calculate it. So f of x is equal to I pi a delta x minus x0 minus delta of x minus x0. Whoops, x plus x0. What's the Fourier transform? F of k. It's integral minus infinity to infinity I pi a times those delta functions times e to the I kx dx. Right? Okay, so there's two integrals. Let's bring the I pi a out in front. And I've got this integral minus infinity to infinity delta of x minus x0 e to the I kx minus this integral delta of x plus x0 e to the I k x0. Sorry, x dx. This is dx. Okay. All right, the first integral, there's a spike at x equals to x0, so that's the only place where the delta function is active. So this is I pi a, and I pick out the value of the function, this function here, when x is equal to x0, so I get e to the I k x0. And in the second one, I get e to the I k minus x0, because the delta function has a spike at minus x0 for the second one, just like that, right? And this is I pi a 2i sine of k x0. Right? And the I times the I gives me minus 1. And so I get minus 2 pi a sine k x0. Okay, this one was a little more complicated, but let's go back and look here at the pair that we have. So first, if f of x is a sine k0x, so we have two pairs. We have a pair that looks like this, a sine k0x is a Fourier transform pair with this function, I pi a delta k minus k0 minus delta k plus k0. And then we also did what if I had this function, I pi a, delta of x minus x0 minus delta of x plus x0? What we found is that that is a Fourier transform pair with this one, 2 pi a sine of k x0. Okay, so you're seeing now we did two examples, right? The first example, we had delta of x and 1, and then we had 1 and 2 pi delta of k. So there was the difference was the factor of 2 pi there. In the second example, if I compare those two, I've got this side, a sine k0, is matching this, a sine kx0, and there's a factor of 2 pi in front again, with a minus sign. Okay, so that the minus sign is there in the second one, but not in the first one. Okay. So you're kind of hopefully noticing a pattern here. And here's the idea. The idea is that if I know one Fourier transform pair, like suppose I know this pair, then actually I know another Fourier transform pair, which is that if I take the function on the right and have it be a function of x, then I can tell you right away what its Fourier transform is. Okay. This is what we call the Fourier transform duality. There's like a symmetry or duality between x and k, so that if I know, in other words, it's like if I know one Fourier transform, actually I've done two at once, because now I already know the Fourier transform of this function. Okay. So let me try to formalize it a little bit. Let's try to prove it in general. So I'm going to try to prove something general. Here's the claim. Suppose you know f of x and f of k are a Fourier transform pair. In other words, f of k is the Fourier transform of f of x. Then you also know that the Fourier transform of this function f of x is 2 pi f of minus k. Okay. So the notation here is a little bit tricky, right? I've got these two functions, f of x and f of k. And I know that f of k, the capital F, is the Fourier transform of the small f. Now, if I had another function which has the same functional form, capital F, but the argument is x, then I know its Fourier transform right away is the function small f with the argument being minus k. Okay, so it's like kind of a mouthful, but it makes sense, at least to me intuitively. It's easier to understand intuitively than it is to write it down. Okay, so let's prove it. Okay, so let's say we assume we already know this Fourier transform pair. So we know f of k is integral minus infinity to infinity f of x e to the I kx dx. And we also know the inverse Fourier transform, f of x is 1 over 2 pi integral minus infinity to infinity f of k e to the minus I kx. Okay, so we know this already, dk. So we know that those two are a pair. Now my question is, what is the Fourier transform of this function f of x? Okay. So it has the same functional form as f of k, but the argument is x. I'm not quite sure what to call this function, because normally I have the function of x is a small letter and the function of f of k is the big letter, and here the function of f has a big letter and I can't make it a bigger letter, right? So I'm going to call it, let's just call it something. I'm really in a bit of a notational bind, so let me just call it f hat. Let's call it f hat of k. That's the Fourier transform of capital F of x. What is that? Well, let's just write it out. F hat of k, that'll be the Fourier transform of the capital F of x, e to the ikx dx. Okay. So far so good. Now let me put in a minus, change the argument to minus k. So what is f hat of minus k? Minus infinity to infinity, f of x, e, now the sign in the exponent will change, e to the minus ikx dx. Okay. And now maybe it helps to change the dummy variable, the integration variable. Let's change it from x to q. So then I have this. Remember, I can rename the variable inside my integral anything I want to. So I'm just changing the variable to q, e to the minus I k q dq. Okay. All right. And now let's change the variable in the function from k to x. Okay. So change the function variable. So f hat of minus x is equal to integral minus infinity to infinity f of q e to the minus I q x dq. And finally, let me change the dummy variable back again from q back to k. Okay, so I did a bunch of like kind of juggling of variables here. F hat of minus x is equal to integral minus infinity to infinity f of q e to the minus I, sorry, I'm changing q to k, kx dk. Okay, but now compare this formula here to the formula that we know from above, this formula for the inverse Fourier transform. It's exactly the same, just missing a factor of 2 pi. So this is equal to 2 pi times f of x. Okay. So what have we got so far? We found that this function, which I called f hat of minus x, is equal to 2 pi times the small f of x. Okay. But that x variable can be anything, so I can also say f hat of minus k is equal to 2 pi f of k. And I can get rid of the minus sign. I can say f of k is equal to 2 pi f of minus k. So what does this mean in words? This thing here we said this was the Fourier transform of the function f of x. And that is equal to two pi times f of minus k. Okay. So that's what we were trying to prove. So let me go back and recap. What was I trying to show? If you know two functions, f of x and f of k, which are Fourier transform pair, then you also know the Fourier transform, which is capital F with the argument replaced by x instead of k. And it's 2 pi times the other function with the argument being minus k. Okay? So I think that's what we just showed, right? The Fourier transform of capital F of x, here, that's what we called f hat of k, is equal to 2 pi times f of minus k. Okay. So it's kind of a mouthful, but it's actually quite useful. And you can use it to do Fourier transforms very quickly. And we'll do an example of this in class where, sometimes if you actually try to calculate the Fourier transform by doing the integral, you end up with a horrible integral. But if you realize that the thing you're doing the Fourier transform of is the inverse Fourier transform of some other function, you can get this answer very, very quickly. Okay, so we'll do this example in class. So I hope you were able to follow all the details here and understand the main idea, and we'll follow this up in class with some more examples, and I'll see you all then. Bye for now.